I will be discussing the problem meeting rooms 2. The problem statement says given an array of meeting time intervals consisting of start and end times S1, E1, S2, E2, SI is less than EI. Find the minimum number of conference rooms required. We need to know what is the maximum number of overlapping meetings at a point in time. The problem asks to determine the minimum number of meeting rooms required to schedule all given meetings without any time conflicts. Each meeting is represented by a start and end time, and two meetings cannot use the same room if their time intervals overlap. A room can be reused only if one meeting ends at or before next meeting starts. The goal is to account for the maximum number of meetings happening at the same time because that number directly determines how many rooms are needed. The solution code separates all meeting start times and end times into two sorted lists and then using a two-pointer sweep line approach. The start array represents when meetings begin and the end array represents when meetings finish. The two pointers S and E move through these arrays if the next meeting starts before the earliest ending meeting finishes. Start of S is less than end of E. A new room is needed, so count active rooms is increased. Otherwise, a meeting has ended and a room is freed, so count is decreased. At each step, RES tracks the maximum number of rooms used at the same time, which is the final answer. Sorting dominates the time complexity, big of n log n, and extra arrays cause big of n space usage. Uh, there is a note that we need to keep in this problem statement while writing the code, that the loop condition should be while s is less than len of intervals to avoid index errors. The patterns which are observed while solving this problem are first sweep line slash event processing, where we convert intervals into events. Start is equal to +1 and end is equal to -1 and tracked active counts over time. Used in Skyline problems, CPU scheduling, calendar conflicts, concurrency tracking. Second is sorting as a pre-processing step. Sorting inputs often transforms a hard problem into a linear scan, very common in interval, greedy and scheduling problems. Third is two-pointer technique, using pointers over two sorted arrays, start, end, to simulate time progression. Shows up in merge problems, window problems, and timeline simulations. Fourth is greedy decisions. Always free a room as soon as the earliest meeting ends. Local optimal choice is global optimal result. Fifth is peak resource usage tracking. The answer is the maximum simultaneous overlap, not total count. Common in bandwidth, memory, server, and room allocation problems. Sixth is state counting instead of explicit assignment. You don't need to assign rooms explicitly, just count how many are active. Reduces the complexity and improves performance. Seventh is transforming the problem space. Instead of working with intervals directly, split them into start or end timelines and a powerful mental model for optimization problems.